Hi, folks. We're going to take a look at chapter 7 in this video, just a quick review of the things that you told me you were most confused about in this week's La Semana. All right, so we're going to start off with taking a look at just a regular double integral, okay? And the purpose of this question is to make a decision which order of integration is going to work best. Like, do I do dx dy or do I do dy dx? Okay. And then the second part of this purpose of this question is going to be that we actually get to work through practicing all of our integration technique. Okay. So two purposes here. All right. So I'm going to write down a double integral. Right? And I know that this is over some region. And the function that I'm integrating is 3 natural log x over 4xy dA. Okay? Now my region, whoops, sorry, my region of integration is an x and a y such that x is between 1 and e, and y is between 1 and e squared. So 1 is less than or equal to y is less than or equal to e squared. Okay. So you might see a question like this, right? We've seen the double integrals and we're given the region that we're integrating over. Now, before we get started, would this be a rectangular region or a general region? Okay. Now, when I look at the bounds, that will actually tell me that this is a rectangular region. And I know that because all of the bounds are numbers, okay? So I've got a 1, an e, another 1, and an e squared. All of those are numbers, which tells us we've got a rectangular region that we're integrating over, okay? All right, so let's set up for a type 1 and a type 2 integral, okay? So I could have x equals 1 to x equals e, and then y equals 1 to y equals e squared of 3 natural log x over 4xy dy dx. That's certainly one option. Or I could have the integral of y equals 1 to y equals e squared, the integral of x equals 1 to x equals e of that same function, dx dy. Okay. So the question here really is, do I want to treat x like a variable first, or do I want to treat y as a variable first? Now, I think to be honest, in this case, it doesn't really matter so much. But what I am going to do, I'm going to do the integration with respect to x first, okay? Now, what that means is I'm going to treat y like a variable just for the first bit. After I integrate, or y is a constant, excuse me, y is going to be a number. I'm going to treat x as a variable. And then after I integrate and I plug in my bounds, then I'm going to go ahead and treat y like a variable. Okay? So let's take a look. I've got the integral of y equals 1 to y equals x or e squared. And I'm going to go ahead and pull out some constants just to make this look a little bit less messy, okay? So I'm going to go ahead and take the 3 on the top out, the 4 on the bottom out, because those are constants, but I'm also going to take the y out of that first integral. Okay, so it's going to look like 3 over 4y. And now I have my integral of x equals 1 to x equals e of what's left. Natural log x over x dx. Okay. Now, I would say this step is kind of optional. It isn't that you have to bring all the constants out to the front, but at least for my brain, it makes the thing that I'm integrating a little bit easier. And it helps me look at it and think, oh, what method do I want to use rather than being completely overwhelmed? Okay. And I look at this and I see, oh, this might be a good case for U substitution, right? So I hope we're sensing a theme. All of these review questions have some kind of U substitution in them, okay? So if I'm going to do U substitution, we can let U equal natural log X. And that's really nice because du is 1 over X dx. So this 1 over X dx gets completely substituted by a du, okay? All right, what does that give us? The integral of y equals 1 to y equals x squared. Got my constants out here, 3 over 4y. Integral of x equals 1 to x equals e of u du, right? That's what I'm actually integrating. All right, so let's actually find our integral now. 3 over 4y. Okay, the integral of u is u squared over 2. So times u squared over 2. And I'm going to plug in x equals e and x equals 1 before I integrate with respect to y. Okay? Now, we know that u is natural log x. So what that gives us is 3 over 8y, right? So the 8 comes from the 4 times the 2. And my u squared is going to be ln of e squared minus ln of 1 squared. Okay, I plugged in my bounds. Now the nice thing is natural log of 1 goes to 0. And the other nice thing is that natural log e goes to 1. So what do I actually have? I have the integral from y equals 1 to y equals e squared of 3 over 8y dy. Okay. Now again, I can imagine, let's pull that 3 over 8 out to the front. We end up with 1 over y. And we know that the integral of 1 over y is just natural log of y. So that gives us 3 over 8 natural log of the absolute value of y. I'm going to plug in e squared, and I'm going to plug in 1. And this gives us 3/8 times natural log of e squared minus natural log of 1. And again, like last time, natural log of 1 is 0. That's really nice. And it turns out that natural log of e squared is 2. And so we end up with 6 over 8, or we could say 3 over 4. Okay. Now on an exam, if you left it like this, 3 over 8 times natural log of e squared minus natural log of 1, that would also be fine. Okay. This is sort of like a little extra bonus simplification level. All right. So I hope this was a good question to get our brains warmed up in terms of how we find a double integral over a rectangular region. Okay, now let's go ahead and do an example where we look at a double integral over a general region. Okay. Now, a lot of people were asking, like, are you going to give us a graph or are you not? And the answer is yes, I will give you a graph. Okay. We still have to be able to pull the important information from the graph, but I'll give you the graph. You just have to be able to do the things with it. Okay. So here's the graph that I'm going to give you. Right? We've got our x, we've got our y, and we've got two functions. All right. The first function is going to be y equals the square root of x. And the second function is going to be y equals x cubed. And they meet at 2 points. The first point is 0, 0, and the second point is 1, 1. Okay? Now, I hope by looking at this picture, we can see that we can set this up as a type 1 integral, and we can set this up as a type 2 integral. All right, so let's practice setting up both ways. Okay, so ultimately, I want us to find the double integral over the following function, x squared minus 3y dA, and I want us to set that up as a type 1 and as a type 2 integral. Okay, so let's get started. For our type 1 integral, we want x equals numbers on our outside. And I can see that I start at x equals 0 and I go all the way to x equals 1. So x equals 0, x equals 1. Now I have to think, oh, what's my top function that's going to go up here? And what's my bottom function that's going to go down here? Okay. And so my top function I can see is the square root of x. That's the red curve. And the bottom function is y equals x cubed. That is the blue one. Okay. And I'm going to integrate 3x squared minus 3y and then dy dx. Okay. That's what we would call a type 1 integral. Well, let's go ahead and set up for a type 2 integral here. That means we need y equals numbers on our outside. And so let's see, our y starts at 0 and it goes all the way to 1. So we go from 0 to 1. And this time, instead of going top bound, bottom bound, I'm going to go right bound, left bound. Okay. So the blue curve is on the right, but another way of saying y equals x cubed is, let's get x by itself. We'll get the cube root of y equals x. That's what we want to call our top bound, okay? So x equals the cube root of y. Now, similarly, we have a left curve, y equals the square root of x, but we want to call it like x equals something. We want to get x by itself before we can plug it into the bounds. So I'm going to square both sides, and I get x equals y squared. And that is going to be my left bound, okay? Same thing, I'm going to do x squared minus 3y, but this time dx, and then dy. Now, I think in this case, it's probably about the same to do these integrals. I think just personally, I would rather work with like a square root rather than a cube root. So I'm going to do the type 1, but if you did the type 2, you should get the same answer, right? And this might not be a bad time to, let's watch Judy do one way and then you do the other way. You should get the same answer, okay? So let's take our type 1 integral. I've got the integral from x equals 0 to x equals 1. All right, let's integrate this with respect to y. So I get x squared y minus 3y squared over 2. I'm going to plug in y equals the square root of x and y equals x cubed dx. All right, the integral from x equals 0 to x equals 1. Let me plug in my bounds. I'm going to get x squared times the square root of x minus 3 times the square root of x squared over 2 minus, now I got to plug in x cubed. So x squared times x cubed minus 3 x cubed squared over 2. And there's a dx squeezed in there. Okay, Well, this looks really messy, but let's clean it up as best we can, right? Let's use our algebra to clean this up a little bit, and I bet it won't be so bad after we do that. Okay, so x squared times x to the 1/2 is x to the 5/2 minus 3x over 2 minus x squared times x to the 3rd is x to the 5th minus 3 over 2 times x to the 3 times 2 is 6. Okay, so I did have to use my exponent rules to simplify here, but once I simplified, now I just have to use power rule, okay? So let's integrate. I get x to the 7/2 over 7/2 minus 3x squared over 2 over 4 minus x to the 6th over 6 minus 3x to the 7th over 2 times 7 is 14. And I want to plug in 0 and I want to plug in 1. Okay, so we're going to get 1 over 7/2 minus 3/4 minus 1/6 minus 3/14, which is really 2 over 7 minus 3 over 4 minus 1 over 6 minus 3 over 14. Whoops, that's a 6, not a 16. Okay. Now, this you could definitely throw onto a calculator. I wouldn't give you something this nasty to simplify on a test, but I think what I really wanted to talk through is that double integral process. Like, how do we set things up and how do we actually do our integration? Okay. So, a couple of things that I maybe should highlight for us. This is the top bound because it's the top function when we're setting it up for type 1. And this is the bottom bound because this is the bottom function when we're setting it up for type 1. Okay? But for the type 2, we've got this one is our right function and this one is our left. Okay, so we're not really looking for a top and bottom with our dy. We actually want to go across, and when we go across, we're going from the right function to the left function. Okay, so let me get this all on one screen for you, but here's an example of a type 1, type 2 setup for a general region. Okay. All right, we're going to do one last example here, and that will be a Lagrange multipliers question, because that was also a pretty popular question that folks had. Okay, so example 3, let's take a look at a Lagrange multipliers, okay? So we've got some function f of xy equals 3x squared plus 6y squared, okay? And we've got a constraint, and our constraint in this case is x plus y minus 90. And it's important for us to keep in mind that that constraint has to equal 0. So if I got like the constraint is x plus y equals 90, I need to subtract that 90 over so that I get the equal 0 part, okay? Now, I'll try and go through these the same way that we did in our lecture video so that they're the same sort of steps here, okay? But if we think back to using our Lagrange multipliers, the first thing that we needed to do was actually what we did right here, which is find our f of xy and our g of xy. Okay, so we already found that. Now we're going to go ahead and find what we call our capital F of xy. Okay. Now, just as a reminder, this is equal to little f of xy plus lambda g of xy, right? And that lambda is our Lagrange multiplier. All right, so this is our Lagrange multiplier, and we're going to multiply it right into our g of xy. And so what do we get? We get f of xy equals 3x squared plus 6y squared plus lambda times x plus y minus 90. And I think that it's usually good practice to kind of distribute out that lambda. So we get lambda x plus lambda y minus 90 lambda. Okay. All right. Step 3. We're going to go ahead and find our partial derivative. So we're going to find fx, fy, and f lambda. Okay. So fx means I take this equation and I treat x like the only variable. When I do that, I had the derivative of 3x squared is 6x plus this one goes to 0. Derivative of lambda x is just lambda. All right. Now I know that all these partials are going to be equal to 0. Okay. So we got fy, right? We go through the same process, but treating y like a variable. We get 12y plus lambda also equals 0. And our last one, we do f lambda. And so 0, 0, and we end up with x plus y minus 90. Okay. So how do we proceed? Well, now we got to solve for our x and y and lambda. And keep in mind, just like our videos from the lecture, it's going to be different algebraic processes. So sometimes it might be elimination, sometimes it might be substitution. But one thing that I find generally very helpful is if I get lambda all by itself, right, in these two equations, I can usually get like x in terms of y or y in terms of x, okay? So 6x plus lambda equals 0 means that lambda equals negative 6x. And similarly, 12y plus lambda equals 0 means that lambda equals negative 12y. Well, if they both equal lambda, then I can say that negative 6x equals negative 12y. And now if I divide both sides by negative 6, I get x equals 2y. Okay? So that's helpful because now I can go to my f lambda equation, which again also equals 0, and plug in x or 2y everywhere I see an x, right? So instead of x plus y minus 90 equals 0, I get 2y plus y minus 90 equals 0, right? So like this substitution, everywhere I see an x, I put a 2y is how I get that 2y in there. All right, well, if I combine my like terms, I end up with 3y. I'm going to add 90 to the other side. I divide by 3, and I get y equals 30. Okay, I found my y. That's great. Now I got to find my x. All right, so I can plug it back into here. X equals 2 times 30. So that means my x will be 60 in this case. Okay. So let me get that all on one page for you. But these should be the same 4 steps that you see in your notes. Don't be afraid to go back to your homework questions, try them again, make sure you're doing them with these 4 steps. And I think that'll help prepare you for the exam next week. Okay. So let me know if you have any other questions, and I will talk to you soon.